Hi, I'm Tom Saladyga. I'm in the Department of Physical and Environmental Sciences at Concord University in Athens, West Virginia. My co-author, Kyle Palmquist, is in the Department of Biological Sciences at Marshall University, and Cassie Bacon recently graduated with an undergraduate degree in biology from Marshall. Our talk today is titled Divergence in the Fire History of Two Mixed Pine Oak Forests, Implications for Prescribed Fire and Forest Resiliency in the Central Appalachians. Before we get started here, I'd like to acknowledge Jim Vanderhorst, who's a plant ecologist with the West Virginia Natural Heritage Program. He was instrumental in helping us identify our study sites in southern West Virginia. I'd also like to acknowledge the Lime Timber Company, who granted us access to our study site in McDowell County in southern West Virginia. Real quickly here, some background and motivation for our project. We're all well aware of the role fire plays in various ecosystems around the planet. Here in Eastern North America, fire exclusion since the early 20th century has resulted in profound changes in forest composition, namely through the process of mesification, where we have reduced oak regeneration and an increase in the cover of mesophytic tree species such as red maple. Now, prescribed fire has more recently been used as a tool to restore some forests in the region, in particular drier pine and pine oak forests. But in the region, there's generally sparse data with regard to fire history and fire ecology in general. And so one of our goals for this project was to identify an area that was lacking fire history data, but also we're incorporating some private lands sites within this project as well. So our research questions centered around a comparative analysis of two mixed pine oak sites with different land management histories. These are located in the Cumberland Mountains ecoregion in southern West Virginia, as I mentioned. And one of our primary goals was to integrate fire history data with fire effects or vegetation data. And through that process, we addressed a few primary questions, namely the historical patterns of fire, including fire frequency and severity, as well as tree age structure, establishment patterns of different species, also tree regeneration and plant species richness at both sites. On the left, you see a map of the Central Appalachian region. In the center are our two sites, Wall Fork, located in Kanawha County, West Virginia, and Height Fork, located in McDowell County, West Virginia. Also shown in the map is the boundary of the Cumberland Mountains ecoregion, which you see here highlights a clustering of large wildfires from the MTBS database. And these are large wildfires greater than 200 hectares during the period 1984 to 2019. On the right, you see two graphs showing population data. The one at the top is population density over time, and the one on the bottom is percent population change. The thing to highlight here is the boom and bust pattern that you see most pronounced in McDowell County, West Virginia, with a rapid rise in population in the early 20th century and a rapid decline as the coal industry declined in the mid 20th century. Looking more closely at our study sites, you see Height Fork on the top on the left and Wall Fork on the bottom on the left. The samples that we collected are highlighted by the red triangles. These are cross-section samples cut from fire-scarred pitch pine and shortleaf pine. The yellow dots indicate the locations of 400 meters squared vegetation plots. On the right, the key here that we wanted to highlight was the difference in land ownership. Height Fork is located in McDowell County, as I mentioned, and that is on the Lime Timber Company private land. Wall Fork is located within Kanawha County, West Virginia, in Kanawha State Forest, and that has been publicly owned since the 1930s. Overall, though, the sites are generally similar in terms of slope, aspect, soil characteristics, the only difference being that Height Fork is slightly higher in elevation. In the field, as I mentioned, we cut samples from fire-scarred pitch and shortleaf pine. You see on the upper left, a partial cross-section removed from that shortleaf pine. And then in the center top, one of the samples that we cut from a different shortleaf pine. On the right top is Cassie standing next to an overstory dominant shortleaf pine. We cored 16 of these at Wall Fork to develop a master dating chronology, which we use to cross-date the fire-scarred samples. On the bottom, you see a series of photos related to the vegetation plots, measuring tree diameter, coring trees for age structure, and tallying seedlings and saplings within the plots. In terms of analysis for fire history, we filtered fire years or fire-scarred years using a 2-scar minimum filter. We calculated fire return intervals and a percentage of trees scarred for those years. We did this for the full comparison period, 1890 to 2020, as well as for 2 socioeconomic eras, boom and bust, 1890 to 1969, and post-industrial, 1970 to 2020. We also compared major fire years to the West Virginia Division of Forestry fire record in order to identify potential cause and likely occurrence of those dated fire years. For vegetation plot data, as I mentioned, we reconstructed tree age structure for pine, oak, shade intolerant, and shade tolerant species, as well as tree regeneration for sapling cover, which included sapling cover and seedling density, as well as plant species richness overall for both sites, as well as by growth form. In terms of our fire history results, you see here examples of partial cross sections cut from shortleaf pine at Height Fork on the left and at Wall Fork on the right. At Height Fork, we collected and dated 36 cross-section samples. These dated from 1818 to 2020. Within that time period, we dated a total of 186 fire scars. 184 of them we were able to identify the season of occurrence. Most of those were dormant season scars, 98%. There were a total of 24 fire years and 18 filtered fire years. And of these filtered fire years, 10 were major fires. And these were years in which more than 25% of the trees were scarred. For those of you not familiar with fire history chart, in the middle of the chart, you see horizontal lines, each one representing an individual tree, the dark or solid tick marks indicating a fire scar. The gray area shows the post-industrial era, which is again 1970 to 2020. And that is just part of the whole comparison period, which stretches from 1890 to 2020. On the lower part of the graph, you can see inverted red triangles, which indicate the major fires that I've already mentioned. And above those major fires, you see a symbol that represents the cause of fire, and these are linked to the West Virginia Division of Forestry fire record. Notable for Height Fork, the last 4 fires, all major fires, were incendiary fires. At Wall Fork, trees were slightly older. The tree ring record spans 1745 to 2020. Within this time period, we dated 77 fire scars. 70 of them we were able to identify season of occurrence, 81% dormant, and 18% growing season scars. There were a total of 29 fire years, 13 filtered fire years, and of those, 3 were major fires. And so again, the inverted red triangles indicate the major fires in the right above the composite. And you also see that the 2007 fire, the cause of fire is lightning. And again, that is sourced from the West Virginia Division of Forestry fire record. In comparing fire return intervals during the full comparison period, we see here that the mean fire interval, the white dots you see in the bar charts there, are relatively similar, 7 years approximately for Height Fork and 12 years for Wall Fork. You see an outlier there for Wall Fork, a fire-free period of approximately 42 years existing at Wall Fork. being the main difference between the sites. If you look just at the boom and bust period, 1890 to 1969, you see that Height Fork and Wall Fork are very similar in terms of mean fire interval. But then as we move to the post-industrial era, Height Fork also remains the same, below 10 years or fewer than 10 years on average between fires. Obviously, the Wall Fork, there was only one fire, so mean fire interval could not be calculated. When we look at the percentage of trees scarred for those filtered fire years during the full comparison period, these values were very similar, no statistical difference between the two sites. You see the average there with the white dots. Approximately 22% on average scarred during fire events at Wall Fork, and approximately 30% trees scarred at Height Fork. Looking at the boom and bust era, again, similar during this early time period, similar to the mean fire interval. The only difference here is the outlier 1953 dormant season fire at Wall Fork, in which approximately 70% of the trees were scarred. Obviously, during the post-industrial era, there's only one fire event at Wall Fork. Important here to note is that the percentage of trees scarred on average nearly tripled at Height Fork from boom and bust to post-industrial. So we end up seeing more severe fires in more recent decades. If we look at the major fires, or only the major fires at both sites, I just wanted to highlight a few years here. First being 1953, that's the only year in which both sites recorded fire. 29% of the trees scarred at Height Fork and 71 at Wall Fork. That is most likely a late fall 1952 fire. That is indicative of the record in which 1952, or the fall of 1952, was one of the largest fire seasons recorded in West Virginia. 2002 is also of note. 92% of the trees were scarred at Height Fork. This likely corresponds to a November 1st, 2001 fire. It was an incendiary fire that burned nearly 2,000 hectares. And then lastly, 2007, which I already mentioned, 34% of the trees at Wall Fork were scarred. These were growing season scars, and the likely cause of fire was lightning, which only burned approximately 20 hectares. In terms of tree age structure, the most important point here is the large pulse in shade-tolerant tree establishment in the 1950s at Wall Fork, followed by subsequent establishment of shade-tolerant trees in the following decades. And so this is obviously very different from Height Fork, in which no shade-tolerant trees were in our data set, and you see a generally consistent establishment of pine as well as oak species at Height Fork. In terms of tree regeneration, just to highlight some of the differences, starting with the sapling cover, we see that there are differences with regard to pine sapling cover, more of it at Height Fork, very little of it at Wall Fork. The other thing to note here in this graph is that most of the shade-tolerant saplings that were observed at Height Fork plots were post-fire resprouts. And so that is linked to those more recent high-severity fires in the fire scar record. Moving down to seedling density, the main difference here, statistically significant difference, is the amount or density of shade-tolerant seedlings at Wall Fork compared to Height Fork. Again, linked to that absence of fire and mesification process at Wall Fork. With plant species richness, the differences are striking here between the two sites. Height Fork overall species richness is approximately double that of Wall Fork. And this is primarily driven by diversity in the understory, herbaceous diversity and shrub diversity. So in summary, in terms of the fire history, first of all, between Height Fork and Wall Fork, during the early socioeconomic era, boom and bust, 1890 to 1969, you have generally a mean fire interval of 7 to 8 years for both sites. Average percentage of trees scarred, 19 to 21%. So very similar in terms of the fire history during this period. As you move into the post-industrial era, though, that's where you have divergence between the two sites. Mean fire interval at Height Fork is 6 years. Average percentage of trees scarred is 58% with 6 fires. You see relatively high pine regen compared to Wall Fork, and herb and shrub richness is up as well. At Wall Fork, obviously we can't calculate mean fire interval with one fire. That one fire scarred 34% of the trees in 2007. Recall that that fire was caused by lightning, and it was relatively small in terms of area. Here at Wall Fork, we have increase in shade-tolerant regeneration. The process of mesification is apparent, and questions regarding the future loss of pine in the absence of fire, we have further investigations to pursue. With that said, other additional questions that we're interested in looking at, the fall versus spring burning question. New research out more recently has investigated the differences between spring and dormant season burning. What we provide here is evidence of the benefits of fall burning. All of the post-industrial fires at Height Fork were fall burns based on, or at least since the 1980s, based on the West Virginia Division of Forestry data. And so we're hoping to investigate that a little further, as well as incendiary fires and the potential to provide randomness or pyrodiversity to the landscape. We are by no means advocating arson as a restoration tactic, but incendiary fires do provide that randomness or pyrodiversity that can help promote resiliency. So resiliency to changes in climatic conditions or insect outbreaks, for example. And so we hope to address some of these questions as we move forward with this project. With that said, if you guys have any questions, we're happy to answer them. My contact information is there, saladyga@concord.edu, and Kyle's is there as well. So please let us know if you have any questions. Thanks for your time.